thanks very much for inviting me to give a talk in the Friend programme. I'm delighted to do so. And I wanted to talk about anthropogenic intensification of these very intense rainfall extremes that cause flash floods in urban areas, and that we've been seeing much more of it, it appears, at least anecdotally, in recent years. So I wanted to start with the very extreme event that we saw in the summer of 2021. Although this wasn't particularly just an urban flash flood, I think that it's really important because it certainly in Europe and particularly in the UK has really made governments think about extreme weather and about climate change. So the German floods were an incredibly intense cut-off low pressure system that caused flash floods across London, lots of basement flooding, flash floods in the Netherlands and Belgium, and then basically hit the Alps and stayed fairly stationary for about 48 hours, causing a huge amount of rainfall and massive but well predicted floods in Germany in 2021. Unfortunately, because of the lack of the warning systems working effectively, they actually caused about 200 deaths. But that wasn't to do with the lack of a good forecast of these floods. I was involved in a rapid attribution study of the floods, and we found that global warming made the heavy summer rainfall between 3 and 19% stronger, and somewhere between 1 and 9 times more likely. And I think the fact that we can now do attribution studies on these types of events is quite exciting as well. And the only reason we're able to do this is because we have these very high resolution convection permitting models that I'm going to talk about later in the talk. And there were a lot of other climate and weather disasters that year as well. And of course, we've seen a number of these extreme events happening around the world and continuing to happen over the last decade, but in particular, the last 3 years have been quite significantly different. And particularly the last year, certainly in terms of some of the heat extremes that have been experienced and some of the rainfall extremes as well, have been significantly different from what we've experienced in the past. So that's really caused a bit of a revolution in governments, and particularly in the UK, it precipitated an inquiry by the Joint Committee on the National Security Strategy. They looked at our readiness for storms ahead, and particularly at critical national infrastructure in the UK. And Dame Margaret Beckett headed that inquiry, and they were quite damning actually in their verdict at the end, and unusual language for a House of Lords and House of Commons joint report. They called for the government to get a grip on climate change impacts. And there's overwhelming evidence that climate change is already having an impact on UK infrastructure. And I think this is really quite clear for other parts of the world as well. And the government must finally recognise that prevention is better than cure and move on from their dangerously reactive approach to risk management. Now, I don't think we've particularly done that very effectively yet in the UK, but I do have hope that at least we've identified some of the issues now. So in this presentation, I really want to go through some of the blue sky science that we understand about this area, what the potential impacts might be, what the climate models are telling us, but then also talk about how we need to use this information to enable some of this adaptation planning that's needed to improve risk management of these types of events. So I think that's really important, that as scientists, we don't just do our science, but we actually make sure that that science is taken through and used in practice. So there's a fundamental relationship between temperature and atmospheric moisture, so-called Clausius-Clapeyron. So that says that as atmospheric temperature rises, the atmosphere can hold about 6.5% more moisture. And this actually is something that seems to hold as well for extreme precipitation intensities. And Kevin Trenberth first came up with this idea in 2003. But there's been subsequently lots of work around the world showing that actually this is a robust relationship, particularly for extreme precipitation intensities. And I suppose this is because extreme precipitation occurs when the atmosphere is saturated. And we found this, or lots of papers have found this in various parts of the world for observations and for climate model simulations as well, particularly convection permitting simulations. The other thing that Kevin stated in his paper is that because intensities are increasing at this fast rate, but energy constraints on the rate of evapotranspiration from the land surface causes total precipitation or average precipitation to increase at a slower rate. This also means that there must be changes in duration and frequency of rainfall to offset these intensity increases. And this actually means that as well as causing more heavy rainstorms and flooding, and you can see an example of the type of storm I'm talking about on the left there. So this is in Canada, and this is the nice thing about Twitter and the internet is, and this is of Instagram, but you can get these really nice visual images of these huge downpours. You can see that somebody's standing in the sun here, watching their neighbor get absolutely drowned in a massive cloud burst. But as well as seeing these very intense rainfall events and the floods that come with them, we're also seeing an increasing number of drought events, you can see there, and also heat waves and other types of extreme weather as well. So there's been a bit of a revolution in climate modelling over the last probably 15 years or so now, where what were originally weather forecast models and very high resolution, sort of 2 kilometre-ish resolution, have actually been taken and forced with greenhouse gases and used as climate models to actually understand more about how convection might change and these convective processes that cause thunderstorms might change in the future climate. We did the first study on this. So Lizzie Kendon led this work and ran this simulation over the southern UK, and it was published in 2014. So that's almost 10 years ago now. It seems like a lifetime ago, where at the time we were trying to produce estimates of change or look at producing information for climate adaptation for rainfall in the summer. And there was really no information coming out of the 12-kilometre regional climate models. There was these very uncertain changes, and you can see that on the left-hand side of the figure there. So the white just shows where there's large uncertainty, no signal of change. What we found when we ran the very high resolution convection permitting model, where we switch off the parameterization on the deep convection, so shallow convection is still parameterized, is that we found a very different signal of change. And actually we found very large increases in these short duration intense rainfall events. So we found this is for the projected change in the 95th percentile of summer heavy 1 hour rainfall events. And we found that the intensity increased around 30 to 70%. It followed approximately Klaus's Clapeyron actually for these short duration events. And the hourly events over 30 millimeters, which is a flash flooding threshold that we use in the UK, showed a 5-fold frequency increase. So I think that the development of these types of models have really revolutionized climate modeling. And from this small experiment that we did in the sort of from about 2010 onwards or something like that, it's really proliferated all over the world now, this idea of using convection permitting climate models. So there's been a number of studies done at continental scales, and I need to update this figure because there's a number of studies now. There's one over South America, there's some over the maritime continent, there's now model domains over the Himalayas as well. And it's really quite impressive now how much work is going into this area and how much information there is from these models on these local scale extreme weather processes that we haven't been able to analyze previously with coarse resolution climate models. The other thing that that my group has been involved in over the last decade or so is collecting together something called the Global Subdaily Rainfall Data Set, and putting, so that's a record of hourly gauges, rainfall gauges across the world. There's about 25,000 that we've collected. We're updating that at the moment to present day, and also collecting additional gauge data. So if anybody's got any hourly gauge data that they would like to share, that would be fantastic. But you can see here, these are the data sets we have at the moment, and this has been really valuable. So together with the new convection permitting models, we've been able to do a lot of work, not just my group, but as an international community over the last decade or so, looking at some of these processes that cause short duration rainfall extremes. And we found that the convection permitting models are really needed for robust projections of changes to the duration and intensity of summer convective rainfall or warm season convection, and that models produce much more realistic extremes, the duration of rainfall, the frequency of events, and the diurnal cycle as well, which is really important. There's now multi-model ensembles of these types of models. I know that the UK Met Office are running a multi-model ensemble over Africa. There's been one run over the UK, and we're planning to run one over Europe at some point as well. So what have we found? So we've firstly, I suppose, found that there will be seasonality changes to extreme precipitation, and this shows results for Europe. So in this presentation, I'll mainly concentrate on work that we've done in Europe, because that's by my group. But there's a lot of work now coming out from these types of models across Africa and more the tropics. I think a lot of the results we've found for Europe are quite similar to what's been found in the US by Andy Prine and his group. In Europe, there'll be seasonality changes. So the season of the maximum 1 hour precipitation event is in the current climate, oftentimes summer for most of Northern Europe at least, and in the Mediterranean it's autumn. You can see that in the future it's changing to become much more dominated by autumn events. This is to do with this extreme drying of the, I suppose, land surface and lack of rainfall in the summer. There's also been quite a bit of work done on the temporal profiles of storms, and this was work done in Australia by Conrad Wasco and Ashish Sharma quite a long time ago now. They split up, using observed gauge data, they split the storm into different parts and looked at how the storm varied. I suppose the proportions of these bins varied with temperature. And they found that as temperature increases, the intense part of the storm gets more intense. And Ashish has recently published something with one of his PhD students looking at this from era 5 data, I think it was, across the world, and found the same sort of signature emerging. There'll also be changes to storm size, as well as this thermodynamic change in intensity. And actually, there's a little bit of uncertainty about what will happen to storm sizes. So in Australia, Conrad Wasco did some work looking at observed gauge data, and they found that the most intense part of the storm increases. And you can see that on the left there. So you're looking at the precipitation amount against the distance from center of the storm, and the red shows the warm storms and the blue shows the cold storms. And you can see that basically the storms are becoming smaller in size but more intense in the center with warming. So Kai Lockbeiler, working with Geert Lenderink, published something using radar data for the Netherlands. in the middle there. They reversed the colour scale very helpfully, and actually their warm storms are blue for some reason in their figure. But you can actually see that they still find this intensification of the storm core, but they also find an increase in the size of the storm in the Netherlands. So warm storms are bigger as well. And then for the USA, Andy Prine did some work on a convection permitting model, and we've done work on this more recently as well, which I'll show in a minute. And he found that storms there are predicted to become more intense in the centre, but also bigger as well in future climates. So when we see warming and have warmer temperatures, we see bigger and more intense storms. So I think the jury's still out a little bit on what will happen to storm size, and I suspect that this will obviously vary regionally depending on moisture availability. So Abdullah Karaman, one of my postdocs based down at the Met Office, did some work looking at changes to storm size and movement as well as intensity with global warming using our convection permitting model runs over Europe. And this was published in GRL in 2021 and actually coincided with the German floods. And so got a lot of press interest. So we found that that the storms were big storms were becoming more frequent, whereas on average storms were becoming slightly smaller. But the interesting finding really was that storms were becoming much more slow moving on average. And actually, these slow-moving storms could become 14 times more common over land by the end of the century in a worst-case scenario. And of course, this is important because the slower the storm moves, the more rain it dumps on a small area, and the greater the risk of serious flooding. And of course, that was also the problem for the German floods that we saw in 2021. And you can see here that as well as seeing this huge increase in the maximum 1 hour precipitation of these mesoscale convective systems, and you can see there on the left that the number of occasions where the hourly rainfall exceeds 150 millimeters in the future simulation is huge. Quite honestly, most of that, of course, is for the Mediterranean region rather than further north in Europe. But you can also see this future increase in slow-moving storms as well. So these future mesoscale convective systems have a preference of slow-moving. And this matters for flood risk, of course. So the implication is that it's important to look at the total event rainfall, including the duration and the spatial extent, as well as the peak intensity to understand changing flood risk. Because if the speed of the storms are changing, as well as their size, all of our flood risk management measures that we use at the moment for point, if we only increase the intensity of these point estimates, we're not going to capture those changes. So, for example, we need to rethink things like aerial reduction factors and other aspects of flood risk management as well. I also wanted to mention urbanization. We've done a study on this for Kuala Lumpur a while ago now, a few years ago, but there's been quite a bit of work done in the American Midwest on this as well. We looked at rainfall data from Kuala Lumpur with a visiting Chinese PhD student, Yafi Li, who led this work, and found that you can see that the urban area of Kuala Lumpur in the yellow in the middle there, and the red dots and the blue triangles show the urban gauges, and the red ones are the rural gauges. And what you can see by the arrows is where there are significant upward trends in extreme rainfall during the study period, which is from 1981 to 2011. And so you can see you're seeing significant upward trends in the urban area. Most of the rural gauges are not showing significant increasing trends. And you can see this more clearly in this figure here, which is showing the increase in the intensity of the 95th percentile of hourly rainfall events. At the top, the urban in the blue line is the average of all the urban gauges and that change over time. And at the bottom, you can see the rural, which doesn't change very significantly. And then you can see the same sort of effects coming out for daily as well. So the daily amounts also show this increase at the extremes for the urban, but not for the rural. And we wanted to try and explain why this was happening. So we did some work with Daniel Argueso, who's now at the University of Palermo in Mallorca. And he ran a convection permitting model using WRF over the maritime continent. So that was a 50-kilometer regional climate model, downscaled to a 10-kilometer domain, and then finally another nesting of a 2-kilometer convection permitting domain within that, which you can see in the top right there. He produced urban and no urban simulations for current climate, for very short simulations, actually, from only 2008 to 2012. But it was enabled us to have a look at the influence of the city on the intense rainfall in that region. We didn't look at future climate change, and this is something we'd be quite interested to look at some point, but haven't had the funding to do so. So what we found was that the presence of the city of Kuala Lumpur itself increases heavy rainfall intensities, and you can see the simulations there and the amount of rainfall produced, and then the difference at the bottom. So the city produces on average about an 11% increase in these 95th percentile hourly rainfall intensities, where there's almost no change over the entire domain as a whole. And that's quite interesting, actually. So that means that, you know, we're not producing more rainfall over the domain, over the city. We're just drawing more moisture from the surrounding area. The actual, the rainfall over the domain does not change, but we're producing more, and particularly more intense rainfall over the city. The largest differences are towards the interior of the urban area, and they're really big, actually. So we're looking at 24% or so increases in that region of the city that's the warmest and probably provides the most uplift. And then we also looked at how the presence of the city alters the local atmospheric vertical structure. And you can see here the blue, so the line at the bottom of each figure shows the land surface, and you can see the orography in black. So the blue is the sea, and the grey is the urban, and the green is sort of rural. So you can see the temperature increase, and that dome of temperature increase over the city, up to about 1,000 meters elevation. And then you can also see a humidity decrease over the city. And that causes an increase the vertical wind speed increases at the bottom over the city, and that causes an increase in moisture convergence. It draws more moisture in from the surrounding areas, which then increases the amount of cloud, water and ice over the city as well, due to that increased moisture convergence. And so all of this basically causes an increase in convection over the city and an increase in intense rainfall. They found similar results over the American Midwest because, in the tropics, you don't tend to get very much wind. So you get the convection forming and then actually the rainfall falling over the city. In the American Midwest, the storms and the convection tends to form over the cities, and then the rainfall falls downstream because of the influence of the wind there as well. And I imagine anywhere in the mid-latitudes that would be the case. It wouldn't be necessarily the case that the convection would fall over the city, but it may be a reason for increased incidence of these types of storms downstream of cities. And maybe something that becomes a bigger problem in the future as we get warmer and warmer temperatures. And it would certainly be interesting to do some future simulations to actually look at some of these effects. And I know that the UK Met Office are working on this at the moment, looking at London, but other cities around Europe as well, the urban heat island effects as well as the precipitation effects. So, I mean, the interesting thing about this, I suppose, is that we can expect small catchments and urban areas to have quite different flood trend magnitudes to larger catchments. And I guess you can see that already. So the effect of urbanization potentially, and the effect of basically concentrating more moisture into these very intense storms, but then taking that away from other places, as Kevin Trenberth first published in 2003. And that, coupled with the increase in evapotranspiration from the land surface caused by increased temperatures, means that these larger catchments may well not have as many floods in the future. So you can see in this diagram here that you get a very positive relationship between precipitation, temperature increases, and precipitation. But actually, the sensitivity of flows in small catchments tends to be negative. It increases quite rapidly for the most extreme events, whereas you can see that actually, because of this reduction in soil moisture caused by the increase in temperature and the increase in potential evapotranspiration, and that effect on the larger catchments, you really do need to get very large precipitation events to cause increases in flow and floods in those larger catchments in future climates. So I wanted to move on to talk about something a little bit different that we've been working on recently, and thinking about large-scale circulation dynamics, because I do actually think that, and work we've done most recently has found that they're very important as well. So far, I've mainly been talking about the thermodynamic signature of extreme rainfall. We know that we will see this intensification with climate change, with warming of about Clausius-Clapeyron, and certainly it can be higher than Clausius-Clapeyron for very short duration events. But large-scale dynamics also matter, and it's much more uncertain what's going to actually happen to these large-scale dynamics. And I would argue that perhaps climate models don't do a good enough job of simulating some of these systems as well, and the changes we're seeing at the moment. So we published a paper earlier this year, which was led by Stephen Chan, who was one of my postdocs, but he's now based at NOC in the UK, where we looked at basically we were trying to work out whether convection permitting models with different structures showed similar results or not in terms of the intensification of mesoscale convective systems across Europe. We looked at two models, so the UK Met Office model and one from ETH Zurich. The difference between the two, they were set up in the same way experimentally, so they had the same resolution, 2.2 kilometers, the same domain. So everything about them was the same, although they were different regional climate models. But one of the other key differences was that the UK Met Office model was driven directly from the boundary conditions from the global climate model. So it also included the dynamical changes from large-scale circulation, whereas the ETH model was a pseudo-global warming model. So it simply took the changes from the global climate model and applied those at the boundaries to look at mainly temperature changes, and it kind of averages those effects on a monthly basis. So we found, I mean, there's some interesting results from this study that really pointed towards the fact that large-scale dynamics are really important for understanding the changes to large storms, and particularly the rainfall that occurs from these large mesoscale convective systems across Europe in future. So we found that in both cases, the top 10% of these mesoscale convective systems produced about 70 to 80% of total precipitation across Europe in summer in both models. And both models showed a large increase in the contribution from high volume mesoscale convective systems in future. And we found, for example, that this almost triples over the British Isles in summer in the UK Met Office model. But interestingly, only the UK Met Office model showed a large increase. So this was about double of these mesoscale convective systems in the future, whereas the ETH pseudo-global warming simulation didn't show a frequency increase. So we think this is important and may suggest the importance of these dynamical changes in terms of the organization of the storms. It seems to be really important. And we know this from observations as well. So I think there needs to be a lot more work in this area, but it's pointing towards the fact that these dynamical changes are also really important, particularly for the frequency changes in the storms, but also potentially for the organization of the storms themselves in the future. So this moving on to sort of go back to what I was talking about at the start of this presentation in terms of the last few summers. This is a slide that Paul Davies, who's the chief meteorologist at the Met Office, produced. It's clear that these large-scale dynamics are really important for persistent weather extremes, at least across the globe. This shows the summer of 2021, and you can see here the blocking pattern and this 5-wave pattern across the globe that's causing these persistent weather extremes all the way from the US-Canadian heat dome on the west there, through the New York floods, the Germany floods, the floods in China, Zhengzhou, and the Siberian wildfires in that year. And you can see the same sort of weather systems occurring in 2022 and again this summer as well. And also actually in the southern hemisphere in the last few warm seasons that they have had, you can see these same sequences of blocks. And we can also start to see this increased blocking again in the winter as well. So this is earlier this year, just before some of the heat waves in southern Europe, or it's just at the same time as the heat wave in southern Europe. We didn't, of course, see a heat wave in the UK this year, but we saw heat waves around the globe. And again, you can see this wave pattern emerging, which I think is probably a pattern 6, perhaps a pattern 7. So really important for extreme weather. And I think we're trying to put together some work at the moment that argues that these wave patterns are also important for these localized subdaily rainfall extremes, as well as the sort of low cutoff lows and high pressure systems that we're seeing. So it's all connected, we would argue, and I'll hope to show you a little bit now about why we think it's connected. So in summer of 2022, we saw the same blocked conditions. They led to a heat dome over Europe. We had 40 degrees C in the UK. It will be interesting to see if this happens again next year. Records were broken in many locations. And of course, we had the same thing happening in 2023. And there have been some interesting pieces of work looking at increasing heat wave trends over the mid-latitudes in Europe. And Europe seems to be a bit of an outlier in this, where there's a much greater trend in the frequency of heat waves and in the intensity of heat waves. You can see that both in the PDFs and in the plots there. This is a paper by Rusi et al. That was published in 2022 in Nature Comms. And this appears to be particularly because of this block that occurs over Eastern Europe and Scandinavia, but also then the fact that a double jet forms because of this. And we were interested in thinking a little bit more about how heat waves might connect up with extreme rainfall events, because they seem to be a connected system. And so I had a PhD student, Christoph Sauter, who's recently graduated, who looked at this globally. So he looked at linking heat waves to intense rainfall by defining heat waves for different locations. So the heat wave was defined as if the daily Tmax lies above its yearly 95th percentile value for at least 3 consecutive days, and the daily Tmin is above its yearly 95th percentile for at least the second and third day. And then it ends when they basically drop below that threshold. And you can see that the last day where the criteria are above on these plots is referred to as day 0. And in the example there, that's actually an example for Australia, where you can see that all of those heat waves that we've defined are actually in their summer from November to March. So if I show you an example from Germany now, you can see this is an example of a heat wave. Again, they're showing the heat wave days up to the last day of 0, and you can see the Tmax and Tmin on the plot there, but also showing the rainfall at that gauge in Germany associated with the ending of that heat wave and the subsequent day. So again, we're looking at rainfall at the hourly. We also looked at the daily scale as well, but particularly interested in hourly rainfall. And it's defined as extreme if it exceeds the 95th percentile for hourly wet amounts. And we use the data from the global subdaily rainfall data set and daily Tmax and Min are from ERA 5. So this is all being published now, actually. So there's a paper for Australia, there's one for global, and there's one looking at the mechanisms behind this as well, which I'm not going to go into in too much detail in this particular presentation, but there's another paper that's just come out recently on that too. And what we found was that, and you can see this in the top right there for Europe, that we're basically in lots of parts of Europe, these extreme rainfall events are much more likely to happen after heat waves, and up to 4 to 8 times more likely in difference to climatology. And particularly when we looked at using different climate zones, we basically found that these compound heat wave extreme rainfall events are more likely in temperate or colder climates, particularly in the mid-latitudes, provided there's no dry season. And that in some parts of the mid-latitudes, 40% of heat waves are actually followed by these hourly rainfall extremes. And that's probably an underestimate as well, because we know that gauge data significantly underestimates the frequency of these types of events, and certainly published a paper on that a few years ago, looking at German and UK radar data. And I think that it was something like 85% of events were missed compared to radar data of these extreme rainfall events. So, you know, that's quite a significant result, that 40% of heat waves are followed by hourly extreme rainfall. And so we can see, for example, the type of event we're talking about here. So we're talking about this type of heat wave. It's a classical omega block, occurred earlier this year. You can see Storm Daniel there as well. These cut-off low systems forming around this omega block, or basically trapped in place by this omega block. And Storm Daniel over Greece there, obviously then went as a tropical cyclone or a medicane across the Mediterranean, hit Libya and caused the devastation there. But before it did that, it had already dropped 3 years worth of rainfall in 2 days over a very wide area. So these blocking heat waves are causing these big cut-off low systems that cause significant spatial extent and massive amounts of flooding, but also are causing these very intense rainstorms as well as they break in a different part of the system. So I think showing the synergy between these different types of events and the compounding nature is really important as we move forwards in this field, and I think it's really important for impacts. We've also been looking at how this relates to synoptic variability by using weather patterns, because obviously it's the whole of this synoptic system that matters for these types of extremes. And in particular, Stephen Chan, again, did some work on this before he left my group earlier this year, and we're still writing up the paper. We found that for observations in Europe and the UK, it's mostly patterns 1, 5 and 6 and 11 from the set of European weather regimes based on mean sea level pressure that have been published by Rob Neal et al. And when we look at future changes of weather from global and regional climate models, we find that those are the types of weather that are due to increase in frequency quite dramatically in the future. And you can see here that then when we look at the annual number of 20 millimeter 3-hour events, or we could look at a higher threshold than this if we wanted to, you can see there that basically we get a big increase in these extreme rainfall events from these types of weather in the future as well. So these types of patterns are going to increase quite significantly in the future, and we can therefore expect the number of these rainfall events to increase as well. And if I finally, before I finish this section, I think it's quite complicated, so it's quite a lot to take in. But basically returning back to our wave pattern, one of my students, Anna Whitford, who's actually due to defend her thesis tomorrow, Friday, is basically has been looking at weather patterns and how they link to hourly rainfall extremes across Europe. But she's also looked at these composite, at the 500 hectopascal level, the composite anomalies of the associated with these weather patterns. And this here shows for weather pattern 5-6, which is one that produces severe storms over the UK. Those, she's taken a composite of the weather patterns that cause more than 40 millimeters of rainfall, and those that don't show rainfall at all. And when you look at the difference, you start to see this wave pattern emerging. So basically what she's found is that, and linking this up to Rossby waves as well, it's really important, this wave pattern in producing these very extreme rainfall events. So we tend to get more of these extreme rainfall events when we have these wave patterns and probably these blocks occurring as well. So there's much more to do here, but just to show the synergy between these different systems, and of course the sequencing of these systems really matters for impacts. And I think we really need to think much more about these compound extremes and also the sequencing and transitions between them when we think about impacts into the future. So I just want to briefly talk about adaptation before I finish. So I've talked quite a lot about science, but I think there's, will climate models ever provide all the answers we need in this space? And I think probably the answer is no. And climate models perhaps need to become much higher resolution, but they're also missing important processes that perhaps we will never capture adequately. So what do we do in terms of providing information for adaptation? Should we just rely on climate models? So we've done quite a bit of work over the last few years producing relevant climate products, and this just gives an example of some work we did using the convection permitting models in a project called Future Drainage across the UK, where we took the convection permitting model outputs from UKCP local, which were at 2.2 kilometre resolution, and we used a very complicated statistical model to estimate different return levels and for different durations and how those would change in the future. We did this in consultation with many different stakeholders across the UK, and this was great because it meant that our work was immediately translated into guidance. So we published the work, and then it was taken up and within a month or two translated into guidance for peak rainfall intensities in the UK for people to actually use for climate change adaptation. And that was because we were working closely with stakeholders and we knew exactly what they needed. So I think this is an important point. So please do work more with stakeholders in terms of translating science through to practice. The other thing I just wanted to mention was, again, about storm profiles. I think that even though we know that all storms don't look like centered profiles, we actually make the assumption in our flood risk estimation methods that they do. And you can see the storm profiles that we use in the UK over on the left of the screen there for the summer and the winter profiles. And these come from the Flood Studies report, which is almost 50 years old now, because it was published the year I was born. There hasn't been updated in this time. You can see that Storm Desmond on the top there, which was a very big storm system that hit the UK, basically doesn't show this centered profile. And you can see on the right plot at the bottom there that if we actually used the FSR method to produce a profile from Storm Desmond, we would get the blue line, but the actual storm looks like the red line. So we have to stop using these centered storms in our flood risk management. And then if we look at real storms, and we've done this for the UK, we've extracted rainfall events associated with annual maxima from 1,300 UK sub-hourly gauges. Basically, short events tend to have very sharp, high intensity front-loaded profiles. As you can see in the diagram, the F2 are the very front-loaded, and you can see the different durations in the colors there. So yellow is short duration all the way through to purple, quite long duration. And we also found that the short front-loaded events can easily exceed the peak intensities of this summer profile that we use. Longer events tend towards flatter centered profiles as it tends to average out over time. But it's really important that we really think about this and also how these storm profiles might change into the future. And I'm doing a bit of work with a PhD student in Germany on this at the moment using a convection permitting model there, and hoping to get that changed in practice. So finally, nod to Ted here, I think that there's lots we need to do in better connecting information from weather forecasting, so numerical weather prediction and climate modeling, looking more at variability and extremes and looking at process pathways. Really trying to understand what the biases are in the different parts of our climate projections by using observations and weather forecasts, which we have all this high resolution information. We can use it to try and understand where the biases might be in our climate models, actually, and to try and understand which bits might be more robust than others, and also to try and integrate all of this information together. And I think that this idea of causal networks and particularly storylines gives a really nice way to actually bring some of that information together from both quantitative routes, from observations, from weather forecasts, from climate models themselves, but also from expert judgment as well, from more qualitative information, to actually provide information on plausible extreme events for risk assessment. And I think it's really important that we start to do this and we don't just rely on information from climate models, because I'm not convinced, I remain unconvinced that they're actually doing a good enough job, particularly at simulating changes to large scale dynamics, but there's lots of other issues with them as well. And I'll probably skip over this one, but we can start to use information from different places to actually set up some of these plausible worst case scenarios. And this is particularly for a winter storm. So in summary, this is from a paper we published in Nature Reviews in 2021, and you can see some of the conclusions there. I think the strong evidence that rainfall extremes increase with regional and global temperature, with even stronger hourly increases. We've got quite a good understanding now of the thermodynamic drivers, particularly from these convection permitting models, but we need to we need to basically have a much better understanding of the large scale circulation potential impacts on changes to rainfall extremes. There's a real need to take this new understanding we have through to updating flood risk estimation methods. And I think that as we move forwards in this field, we really need to be thinking much more about compound extremes. They're very important for impacts, and they may change much more than individual extremes with warming. I think they're often connected by physical processes in sequences that might be important for impacts and that we neglect in our current analysis methods. Global climate models appear to be underestimating or potentially underestimating the changes we're seeing in the real world. I think particularly the persistence of block conditions, and these are important for heat waves and extreme rainfall. And as I've said already, I think that we need to basically be thinking about combining information from many different sources, together with expert judgment and qualitative information as well, to provide estimates of worst case events for adaptation planning. So I'm going to finish there, and I'll take any questions. Thanks very much.